Hi all, hope you've had an okay week. It's time to get on with our Friday lecture. Hopefully everything's working. I see Leo said that things weren't working on streams. I think they're fixed now. I hope so. They just weren't published the way they were supposed to be, but they should be good now. Just let me know if you can't see them on streams. So let's move on. First, a little bit of admin, and then we're going to pick up where we left off on the last lecture. Just want to remind you all about academic integrity. I don't want to say anything more about it except that you should all be thoughtful about that. You should know what's said on the course webpage, and you should know it applies to the assignments and to the exams, to everything you do in this course. Reminder about the mid-semester exam. Mid-semester exams on Monday. You're going to get 4 questions. The first, they get progressively more difficult. The first couple of questions everyone should find them very quick and fairly easy to do. I hope everyone in the class will get those first 2 questions out. The next question will be a little bit harder, and the last question will be quite hard, okay? And remember, when you're doing these tests, you'll get marks for whichever unit tests you pass. So be thoughtful about that, because it may be that even some of the harder questions, you can get 1 or 2 marks by addressing the simplest parts of the question. So make sure you're strategic and you use your time wisely, and don't forget you can get marks for fairly simple parts of the questions if you look at how the unit what the questions are asking you to do. So just think about that when you do the exam. All right, I'm going to move on. Where we left off was collections. Do you get marked on coding style? People have asked that many times, and the answer is no, you do not get marked on coding style because it's an auto-graded exam. Okay. It's an auto-graded exam, folks. A machine is marking your exam. I will check some of the exams, but you won't get penalized for your coding style. I did actually tell you this in the last lecture, I believe. So we're talking today about J14. We're continuing where we left off, and we're looking at the collections framework. And I explained to you, I'll just recap some stuff here. I explained to you, first of all, there's this idea of a set of interfaces that define a set of behaviors for collections that Java provides. These are part of Java. This is part of the Java standard library. Then underneath the you had a horrible exam in 1600. Our exams are never horrible. Hopefully you'll find the 1110 exam less horrible. But please, I just saw your comment there. I just want to make sure your expectations are right. You should never expect, certainly in 1110 and perhaps in 1600, you shouldn't expect to be getting full marks for any of these tests, okay? They should be rare to get full marks, okay? So you should expect, if you're an average student, you should be expecting to get 60%, right? Or maybe 65 or maybe 70 or something like that, in that ballpark, right? If you're an outstanding student, maybe you're going to get 90%. Now, if you've done extremely well, maybe you'll get 100%. Okay, that should be roughly where your expectations are. You should expect everyone in this class, everyone who's still here, everyone who has gotten through assignment 1, you should all expect to pass. Okay, so I don't expect any of you will not pass. I hope very few of them you won't pass. Okay. The exam runs for 30 minutes. It's all on the course webpage. Let me just be completely clear. We're still getting questions here. Course webpage. Let's go here. Assessments. Mid-semester exam. There. 30 minutes. All the details here. The exact start time and everything. You should go through here. Notice that the sample exam I've put here is for a previous year. Okay? And I explain here the difference between what happened in previous years and what we're doing this year. This year's different because of COVID, because of the way we're running it, okay? And I explained to you here what the difference is. I didn't make you a sample exam just for this semester. So you look at last year's sample exam and you can see here what the relationship is between the sample exam and what you're going to get, okay? Please read this. Please look at the sample exam, and that should give you a very good guide, okay? The level of difficulty, etc., is not going to be different, okay? 30-minute exam. All the details are there, okay? Now let's go back to where we were. Okay, I was talking about collections. We've got interfaces, okay, which describe the basic behaviors, and then we've got concrete implementations. And the idea is different implementations will have different pros and cons, but they're going to implement the same interface. So they'll provide you the same behavior, they'll just implement that behavior differently. And that's because there's often trade-offs that are made when you build something, and Java allows you to choose between the different trade-offs, which have different performance characteristics. And which one do you choose? Well, that's a very interesting question. And one of the things we're going to do in this class is you're going to build these things from scratch yourselves. And by doing that, you'll get a much better understanding about what trade-offs are being made in these things. Now I should have had the slides here for you all. There they are. There's the slides. So collections framework, and yeah, and whoops, press the wrong button. There we are. So we're in J14. We're in the collections framework, and there's some basic operators. I'm just recapping what we did last lecture. So I'm just going to go through this very, very fast. This is the key thing. You've got these interfaces: set, list, queue, and map, and then you've got concrete implementations all through here. And we're going to do hash, hash set, tree set, hash map, a tree map, and we're going to do array list and linked list in this class this semester. You need to know about all these things, but those ones I just mentioned, we're going to go into a great detail later on in the semester. This is important. We're going to deal with this in a few moments. Ordering collections. If a type implements a comparable interface, right, then it will have a compare to function, and that allows you to compare two instances of that type. So you've got two bikes. If the bike type implements comparable, you'll have a compare to thing and allow you to compare this bike with the other bike. We often use the variable name O or other to refer to something else when you're comparing two things of the same type. So you see there TO means T other, the other one. Okay, you want to compare two bikes. How do you order them? Okay, interesting question. How do you order them? Maybe you do it by serial number. The one with the lower serial number comes first. I don't know. It's up to you. But for any given type, you can define your own, what they call natural ordering. So when anyone ever has an instance of this type, like a bike or a COMP1110 student or a person, you can compare them using, if they implement the comparable interface, according to whatever the type says. In addition to that, you can also build your own comparator, which allows you to compare two instances. And we're going to do both these in a few minutes. And you can sort them using lambda expressions. Isn't the in-object method standard within classes? I'm not sure what you're referring to. All right, let's move on. Back to the code, which is where we were. Now, we were here. We were running this code. So we had this code here. We created ourselves an array of students. There they are there. We made them. We printed them out as members of an array. We then create a list called students out of the array using a special thing that in the arrays class called asList, which converts an array into a list. And so we have the list here, students. And then we went through the list, and we noticed that these two things are in the same order, okay? Because lists maintain order. Then what we did is we created a map, and a map that mapped UIDs of the students to the students. And so then we put all the students in the map by finding their UID and attaching their UID to them, okay? So each entry in the map had a UID and the student, okay? Then we went and manually added one. Oh, then we looked up one. We looked up this student here, and we found that student in the map. You say get, and then that's what we call key value pairs. That we put in the key and we get out a value. Okay, so we put in the key. The key was this thing. We get out the value, and we found that value. And then we have here. We've gone and made a new student. We've called them Sue, and we've gone and added them. And those of you who had sharp eyes noticed I made a mistake. That was on purpose. I deliberately here, when I did the lecture last time, I put in someone else's UID. I didn't put in this UID. I put a different student's UID, and that squashed the other student's entry in the map. Okay, because now there were one key previously pointed to, I think, the student VJ, and now was referring to Sue. Okay, so when you say put, if you have the same key that's already in there, you'll squash what's already in there. But we fixed the bug by changing this to use Sue's UID, which was different to VJ's UID. Okay, and then we went through them. If you look at the video, you'll see me go through all that. Okay, and that's where we're up to. Okay, so let's just run this. I've just quickly recapped everything we're up to, and we've added Sue, and that's our map. So there's our map, and it's got Sue is the new one added to it. Previously, Sue clobbered VJ, but now we have all of them, and then we now have 5. And that's where we left off. So what we're going to do now is do this ordering thing. Okay, so let me just check. Yep, that's where we're up to. So what we're going to do now is we're going to do ordering. So we're going to use sorting and so forth. So let's do that. So what we can do is we can sort the students, but so you can go like this. You can say collections. Just need to mute that laptop. You can say collections. There we are, which is Java util, which is part of the Java standard libraries. There it is, collections.sort. students. Okay, oops, there we are, like that. So that will sort the students. Okay, now you'll notice there's a red line there. What does the red line say? So let's put the mouse over the top of it, see what it says. Have a look at it. It says, it's a long error message, but the bottom line is our students class doesn't implement the comparable interface. And I explained in the lecture just a few minutes ago, we need to do that if we want to better compare two students and put an order on them. So how do I know which order comes first? If I want to sort my students, how do I do it? Well, Java doesn't just automatically know that, so we have to tell it. And the way we do that is by implementing the comparable interface. So let's go and add that to our student, which was, where are they? They're there, but we might as well add it to person. So we can do that because student inherits from person. So there they are, there's the person. So what we can do now is we can add to person the ability to compare things. Okay, so let's do that. Yep, and yeah, I already answered the question about the exam. Indexing. What's the question about indexing, Darren? I don't understand. You've said indexing. But I did say the questions about the exam should be sorted because it's all very clear on the web page. Implements. Comparable. Parable. And then we'll say person. Whoops. If I can just type. There you go. Like that. And then, all right, so now what's the matter? The problem is, why is it complaining? Does anyone know why it's complaining? It's complaining because we haven't implemented the method for comparable, because it's an interface. It says, you've got a contract, you're going to be comparable, which means you're going to implement a particular method. IntelliJ tells us that, so we can just click on this button here, and it will add it in. There it is, okay? So now it's allowing us to compare this person, whichever person that is, with another. It says oh, we often say other. Let's do that for clarity, other. Okay, so it's us and the other, okay? This and other. So now we have to have a way of comparing two people. And what we need to be able to do is return an integer which is greater than or less than according to our criteria, okay? So one way to do it is we can say, we can just do the following. We could say something like, we can return the age, our age, minus the other person's age. Okay, and what that's going to do is it's going to, if the two are equal, then that means they'll be equal in order. And if they're not equal, then whichever one is the lower will be a negative. Sorry, whichever one is the lower, it will have a negative number. Okay, so that will allow us to rank all the people by their age. We can make this fancier in a moment. All right, so someone's complaining about 30-minute exams. I could give you a 6-hour exam, Yufan. Would you like that? Having a short exam is a plus and a minus. The mid-semester exam in this course is always 30 minutes, and it's done like that for a good reason. It's worth only five marks, this exam, and it's for you to sit down and focus for 30 minutes and try and answer a bunch of questions, okay? You'll find that that'll be enough. If you're on top of the material, you'll be fine. Okay, now let's go and do what I was about to do here. So if people could just keep the discussion on the chat to the lecture, I'd really appreciate it. Okay. So what we're going to do now is notice now the red squiggly line. The red squiggly line has disappeared from students. Okay, so now it's happy. Why? Because we just went and implemented the comparable interface on the person. That's what we just did there. Okay, so now we can now sort this thing. So now supposedly our collection is sorted, and we can go and print everything out again. I'll just paste this code. So sorted. So all students, in what order? It's in the natural order. What we call the natural order, meaning that we're sorting it in the order that the class provides. We can do it in other orders as well, which we'll do in a moment. But right now we're just sorted in the so-called natural order, like that, and so like that. That's all we need to do from that. from list. Actually, we want to do it from the list, don't we? Students here. Like this. Okay, so what we're doing here is instead of doing it from the UID map, which is the code I just accidentally copied, we're going to go to this list here. That's a list. We've sorted the list, and now we're going to go through all the students in that list in order. Or from sorted list, just to get my grammar a bit more sensible. From sorted list, like that. Okay, let's run it now. And what we should see is that everyone is sorted according to what we did here, which was do it by age. We're comparing people and we're sorting them on the basis of their age. Run this here, and we should see everyone sorted by age. Okay, there it is. And lo and behold, we see VJ, Mary, Bob, and Ting. We don't have Sue because Sue isn't in the list because Sue's only in the map. Okay, I didn't add Sue to the list. If we added Sue to the list, Sue would be in there as well. But we see them, they're now sorted by age. Now, if we were to go and make, let's add Sue to the list. Let's do that. Let's add that. I didn't do this before. Let's just add this, add Sue in. Say, before we students.add students.add Sue. Okay, so now Sue's in the list. Run it again. What's interesting about Sue, Sue's got the same age as someone else, I think. Yeah, no, not Darren asked, does it need to be made comparable to use collections? No, it needs to have the comparable interface if you want to sort it. Okay, if you want to sort it. If you want to do this, this is what requires us to have the comparable interface. This is sorting a collection, so this is a collection. Students is a collection. Whether or not you are comparable doesn't matter. But if you want to sort that collection, then you do need comparable, okay? Because otherwise Java doesn't know how you want to order things, right? So when you implement comparable, it's your way of saying, I want to order it this way, okay? So let's go and run this again, or did I just do that? All right, so I've just run it again. Notice that Ting and Sue here have the same age, and we're sorting by age, right? So 18, 19, 20, 21, 21, right? But what we could do, if we want to make this a little bit nicer, is we could sort, say, okay, they've got the same age, let's sort by something else. So we'll say if age equals other.age, meaning these two things have the same age, then we'll use something else to sort on. Let's sort by name, for example. So we can say return, and we can say name dot compare to, because name implements a compare to. It's string implements a compare to. String is a standard Java type, so it's got the compare to interface. And we can say other.name, other.name. There we are. So now what that means is if they have the same name, then we want to order them by, if they have the same age, then we want to order them by name. So let's just run that again. And we should see these are ordered by name, and we see Sue in front of Ting now, okay? Because S comes before T. All right, and what else did I want to do? Oh, we can do other orderings, so let's just quickly do that. Now, so that was the so-called where am I? Okay, so that was the so-called natural ordering. That's an ordering that's built into the class, into the COMP1110 student class, or in this case, the parent of COMP1110 student, which was person, okay? Notice that COMP1110 student inherits its parents' behaviors, okay? All compared to functions return int. As far as I know, Nathan, that's a sort of question that I would have to check to find out. But yeah, but if memory serves, that's correct. They return an int. And if it's 0, it means that the two things were the same. And if it's positive, it means one was higher. If it's negative, it means the other was higher. It's just a convention. Okay, so now what we're going to do is we're going to sort according to some other order. So what's a natural ordering to sort students in other than their age? Can anyone suggest? So age is a good one for people, right? So people had, let's have a look at the properties of a person. A person, what do they have? They've just got an age and a name. That's the only thing we have, right? Yeah, so Darren says, why don't we sort by UID? We can do exactly that, okay? We can support by UID. So, but a person we can't sort by UID because they don't have a UID, but a student does. So let's go back here and we can sort this by UID. How do I do that? Well, I can't use this. Well, we could change the natural ordering for students if we wanted to, but instead what we're going to do is... sorry, I've just got a doctor calling me. My daughter hurt her arm, had to get an x-ray. Sorry for that interruption. Where were we? That's the natural ordering. We can sort these by whatever orderings we want. So let's sort by UID. But because the natural ordering is already defined, we just did that a moment ago by sorting by age and name, what we're going to do now is we're going to sort by UID, as someone suggested on the chat. Okay? And here we go. And the way we do that, we've got to provide some behavior which describes the ordering. Okay? And how do you provide behavior in Java? We just learned this a little while ago. Yes, that's exactly what I'm saying. We just did change the ordering. Someone's asking, can you provide another ordering? And that's exactly what we have here. We just changed the ordering. So it used age and then it used name. We could make whatever ordering we wanted to. But for a person, the only things we have to use is these two fields here, age and name. For a student, we can do something else and we can make it do something specific. And I'm just getting to that right now. The question is, how do we do that? How do we provide behavior in Java? That's a simple question. Folks, how do we provide behavior? We do it with a lambda, okay? So we do it with the lambda. So we can write a lambda and say, use this lambda to do the sorting, okay? And that's what we're going to do now. So now we're going to say all students in UID order, as someone suggested, UID order. And what we're going to do is we're going to resort it. So we're going to say collections dot sort, but instead of just going like this, which will do the natural ordering, we're going to provide another argument, which is the lambda. And that lambda is going to take two arguments. What are the two arguments likely to be for a comparison? The two types, right? So we're going to say COMP1110 student and COMP1110 student at the two types. Okay, sorry, we've got to give them names. So we're going to call them S1 and S2. That's the two students, S1, S2. All right, so that's two students. And we're going to return, so we're writing a lambda expression here, return, all we need to do now is do a compare to on the strings of the UIDs, okay? Because UIDs in our class were done as strings, and strings already have, the Java lang string already has a compare to function. So we can just compare those two strings using the compare to. So we say s1.getUID, and we say compare to, there it is, IntelliJ is already figuring this out for us, s2.getUID. Okay, and what that's going to do is it's going to compare the two things in that order. Why? I need to put a semicolon at the end of this. That's the problem. There we are, semicolon, and a semicolon there, and that should have sorted it. Why is it all grey? I don't know why it's all gone grey. That's strange. Anyway, there we are. So we have a we now have our thing hopefully sorted by UID. Let's run this. Class list, and yeah, indeed, it's done the right thing here, and you can see it down here from VJ and Sue. They're different by just one digit. Okay, so now we've sorted by UID order just like that, and the way we did it was here we just provide the students and use their natural ordering, no other argument. This time we provided a lambda, right, as a second argument. It says do it this way, don't just use the natural ordering, use this ordering. Okay, and we can do the same thing. We can do something like, we can basically repeat this and say, oh, let's use their marks, right? You can sort them by their grades. Remember, these people all have grades. There's their grades there, and we can sort by that grade. So let's do that. Where are we? By grade order. Okay, and then to do that we need to change this and say get mark, I think, is it, or is it just mark? Like that. There it is. Or how do I do that? S1.mark. What's happened here? S1 dot, or get mark, is it? We don't have such a method? Huh, let me have a look. I thought we did. COMP1110 student. Yeah, we do. Oh, it's private. So we need to change that from not being private. Okay, we'll make it public. Okay, so it didn't like that because that was private, and now it's happy. Okay, and now we say, oh, and we don't do a compare to now because these are just actually integers. We can just do a subtraction. So return S1 mark minus S2 mark. And have I got the parentheses right? I think I have actually. No. There. Okay, great. So what that's going to do is we've got a new comparison function. That'll take two students, one student, student 1, another student, student 2, and then it's going to return the subtraction of student 1's mark from student 2's mark, which will cause to do a comparison based on based on their marks. Okay, so now we're doing them in grade order or mark order. And let's have a look at this. And lo and behold, we've done exactly that. Okay, so Mary got the lowest grade, Sue got the highest grade, and they're sorted according to that. All right, we're done with sorting. Now we get to do the really fun part of this lecture, which will take a while. We're not going to finish this today. We'll end up finishing it tomorrow, I think. Not tomorrow. Yeah, well, unless you want to come on Saturday to the class. But we'll do this. It'll probably extend to Monday. This is a huge thing. What we're going to do now is something I promised you before. We're going to solve Boggle. Okay, so let's actually go to here. Remind you all of what Boggle is. Where's the Wikipedia page? Somewhere here. There it is. Okay. There we go. And that's the Boggle game. I've explained this to you before. What we're going to do is we're going to write something that solves it. This is a useful thing to do. You had to do this for the advanced part of assignment 1. You have to do this for assignment 2. How do you solve the game? That means how do you find solutions? To do that, you need to do a search. Okay, and so we got. All right, so let's get on with that. This is going to be a big task. We're going to start with. All right, so hopefully everyone understands what we're going to do. Okay, we're going to create this game. We already created the game in a previous class, and by making the dice randomly roll themselves, just like you see there. But what we're going to do in this class is we're going to find all of the words that solve Boggle. And remember the rules for Boggle, the words have to be linked, so you can so you have to be able to draw a line between the dice to do it. Okay, so you could do the word. Let's just go through some of the words. GET is get, SET is set, NET is net. What else we got here? You can NO is no, and so forth. But I think there's a minimum word length. The minimum word length is 3, so NO wouldn't work. Okay, so that's actually not a legal Boggle word. All right, so we wouldn't include that. And SO is so. That's not a legal Boggle word either because it's S and O. So the connection between these dice is done either direct side by side or diagonally. Okay, so NET is fine and SET is fine and so forth. And GET get. All right, and you could do gent GENT, right? And you could do went? Yes, you can. You can do went, WENT, went. All right, so that's the way you make words. You can't go to a letter twice, right? Once you visited it, you're done, okay, on a given search. All right, so what we need to do now is we've got to work out how to solve this. So it's a search problem. So basically what we need to do, the way we're going to do this is look exhaustively. So we'll start at a dice like this and say, what words can we find from here? Oh, we go here. That's not far enough. It's only two letters. We go here. Is TEG a word? TEG. That's not a word. You can keep going. TEGO. You keep going. TEGO and so forth. And keep looking and see if they're real words. So you'll need a dictionary to look the words up to see if they're actually real words. And we can think of some fancy ways to make this a little bit faster. But that's the basic idea just there. So let's go back. Where the heck was the where was it? The Boggle. There it is. Okay, we're going to copy this. Copy that class there because we're going to pinch some stuff out of it to make our task a little bit simpler. Boggle, we're going to paste that in there. There it is. Add it, and let's have a look. Okay, so this is the one we did before. Let's just run this. Very simple. Run Boggle. All this one is doing is we're running it there. Okay, so there it is. What Boggle is doing is it is taking these are the dice. So there's 16 of them. Each has 6 sides, right? And these happen to be the actual dice that are in the real game of Boggle. And then we're using random here. And then we're going through and picking one of these dice at random. And then we're rolling that dice. And then we're producing this grid here, which is just like in that picture you saw a moment ago. Just like this. Okay? So that's the basic idea. And what we want to do now is not this, but actually to try and solve the game. And we're going to try and apply the test-driven development idea that we just learnt in the previous lecture. Okay, so let's get started. This is a big and difficult lecture, and it's kind of fun because I could get everything wrong, which will be kind of bad. But I've got some notes here. Hopefully, we'll go okay. What we're going to do is we're going to, like I said, we're going to use test-driven development as we do this, because that's what we're going to try and do for the rest of the semester now. I'm just going to indent this thing. How do you do that? I always forget the keystrokes for this. Reformat code, there you go. Get rid of the indents, right? Okay, so we don't really want this. What we will do is we will refactor this code and make ourselves a function here, static char like this, and we'll call it shake. So this is like shaking the dice, right? And we will pretty much move all this stuff here. Copy and paste in here. Okay, there it is, and this is going to return. We want to return the dice, which it's not doing yet. Okay, so what we really want to do is create ourselves a results array. So say char like that, result equals new char 16, right? And instead of printing them out, which is what we're doing here, we'll just so this here is all the printing. Let's just comment that out for the minute because we might use that code later somewhere else. So what we're doing here is we're instead we're going to put them into the result. So we'll say result I. So we're going through this loop 16 times. We're going to say result I equals whatever we just got, which was value. Okay. So instead of printing this stuff out, we're going to return ourselves an array of characters. All right, this is a very, very small change here. Would it be better to use a 2D array? Maybe, maybe not. Okay, this is an interesting question. Java doesn't do 2D arrays all that well, so it's interesting. Really good question there as to whether we should use a 2D array or a 1D array. If you're comfortable with doing the arithmetic of the integer division and integer remainder, it might be faster and simpler to do it using a 1D array, but that's a great question, okay? And it doesn't have a simple answer. So sorry, I can't give you a simple yes or no, but that's where we are. Now what we can do, we can write a little print thing. Let's write another function called print Boggle, right? Static void print Boggle. And we'll take an array like that, char, like that. Oops. If I could just type Boggle like that. So we're going to print this thing out, whatever we get given. And we'll just borrow the same code pretty much. We're just going to go through here and print out all 16 elements and use this magic here to get it formatting nicely in a little square like we saw in the, oops, like that. Get rid of these comments. Okay, so once I've done this, we should be pretty much back to where we started. We've just factored things out a bit. And we've got row length and we've got value here. So what we want to do is we want to, instead of saying value, we're going to say Boggle I. And row length, where did we do row length? Oh, we did it up there, okay. It doesn't get used there, but does get used here. So you can just grab this and put it here. There it is. Okay, that should work. Now we just need to, all right, tidy this code up a tiny bit. So now instead of this main method doing it all explicitly like that, we're just going to actually call a function. We don't need that. We're going to say char like that, Boggle equals shake, right? So that will give us 16 values, and then we can say print Boggle shake, Boggle, right, like that. Okay, and then we can run this and we should get exactly what we saw before. Now notice, one thing to notice here is that each time I run this, of course, we get different values, which is exactly what you want in a real game, right? But one of the challenges is that's often not so great for debugging. Okay, not so great for debugging because you often want things to be the same every time. So you may not want to do that. And one way you can change that, by the way, we may not do that here, but what you can do is you can provide what's called a seed into the random number generator. Now what happens is every time you run it, it will produce a random result, but it'll always do the same result. Okay? So it'll still be randomized, but every time it's going to be exactly the same. So I'll run this multiple times to get the same result. Okay, we'll get rid of that for now because we're going to take a different approach, but that's a useful trick and it may be useful for you. It could be useful in your game, perhaps 1140, just useful to have the idea that using a random seed can make something that's supposed to be random behave the same way every time you run the program, just so you can do debugging. All right. Now, what are we going to do? Let's write some. Let's write ourselves a little test that is going to test whether or not we've got a good result. Okay, where have I done this? I've got a whole bunch of notes here that I wrote, and here we are. So let's write ourselves a little test function, because remember, test-driven development says write your test first, make sure it fails, then write the code that makes it succeed. Okay, so we're going to write the test first, and so we're going to say at test, oops, like that, and then we're going to write something called test Boggle, public void test Boggle, and we're going to write ourselves a test. And so the first thing we're going to do is going to make ourselves a here. Yeah, what we'll do is we'll just write those letters in their order, right? And if you have your web browser open, you can go and look at that there, and you can start writing in the chat any words you can see there that are 3 letters or more. You can write them in the chat, okay? And then we can test for them, right? So if you see a real word in there that has more than 3 or more letters in it, in this thing, if you open this up on your browser, what we'll do is we'll see if our solver can find it, right? Because it should be able to find it if our solver is correct. Okay, so we're going to write test in a moment, and I'll let you type away while I start typing some other stuff, right? Now I'm going to write those letters in, R, H, R, E. Of course, if I make a mistake here, please yell at me. H, comma, R, comma, E, like that. YPCS, Y, comma, P, oops, comma, C, comma, S, oops, S, like that. And then we've got, after that, we've got WNSN, comma, W, S, was it WS? Yep. N, sorry, WNSN, WN, comma, S, N, like that. And then TEGO. Okay, then followed by T, oops, T, EGO, E, G, O, like that. Okay, and so that should be correct. Yell at me if I'm wrong. And we've only got one word. Come on, folks, you can do better than that. One word. Testing for JavaFX is another whole thing, so let's have that discussion later. But you guys are supposed to be coming up with words. I've only got one word there. That's press. You should be able to find more words than that. Now what we should be able to do is we should be able to write ourselves imagine we had a thing here. Remember, when you do testing, when you do this sort of programming, you have to kind of suspend disbelief and imagine it's already there and all working. So let's write something here. List of strings. Solve Boggle, and we'll give Boggle the dice, char, like that, dice, okay? Or we'll call it Boggle. Okay, and then we'll say return null, because we haven't implemented it yet, okay? And then it's asking up here if that's the one we want, and it is indeed the one we want. There it is. Okay, so this solve Boggle thing, which doesn't exist yet, will give us a list of all the solutions. Now, I've only got one word. Come on, folks, you should be able to do better than that. Just go to that Wikipedia page and tell me more words that you can see there. And now what we're going to do is we're going to say, and I also want words that look like they should be there, but are not legal words for whatever reason, like maybe they're not close to each other or something, and you can tell me them as well. All right, so we're going to say assert true, did not contain, and then we'll say the example we have there is press. Now, is my cursor just not behaving? Oh, maybe my Teams is not up. Oh, there we go. Okay, all right. Sorry, you guys sent a bunch of words. I apologize. Just Teams was misbehaving. Great, terrific. Okay, you don't need to tell me more words now. Okay, you can tell me more not words. All right, so it does not contain press, and then we'll say we're now going to use our collection, right? So notice here, the Boggle is going to return a collection type called a list, and we can now ask if something's in the list by saying contains, right? So we can say result. We haven't actually done it yet, so we say list of strings. Result equals solve Boggle with our dice, okay, like that. And then we'll say result dot contains press, right? And it should be there, okay? If it's not there, we've got a problem. All right. Okay, and then let's just multiply this out a few times over. What are the other words you got there? Gent, pry. Why is it giving me an error here? Oh, missing a closing parenthesis there. So gent, what else you got there? Pry, song, ire. Pry. Okay, maybe I'm not going to get all your words in. You guys outdid me there. Missing a closing bracket. Missing a closing bracket. What's the longest one on that list there? Let me see if there's any. Have you got any longer words than 5 letters? Anyone get a longer one? Center. Well, that's good. Let's see if we can do center. Okay, and then we'll finish there, and then we'll do some that shouldn't be in there, right? So center. Okay, there it is. So center, and now what we want is a list of ones that should not be in there. Let's have a look at what have you said here. Sent. Someone said sent. That's good. It's a snog. We've got tons of words. Okay, good. What word should not be there? Steve Blackman should not be there. Yeah, not a word. Present. Okay, and what's good to have is words that look like they should be there, like maybe all the letters are there, but they're not joined up properly. Okay, is respect actually in there, or is that a word that can't be there? That's a good word. Is that a not word, or is that a valid word? Let's just type that in because I like that. Respect. That's our longest word so far. All right, very good. And then we want some assert falses for ones that are not. Okay, and the one we got there, one of them we got was present. Assert false. False is yep, we're going to add that in. There it is, and it was present, right? What else have we got there? Ones that are not words. Center isn't a valid word. Okay, so that should be assert false. I don't have the picture in front of me, so I'm just taking your word for it. False. Are there any others that are not? Neither is rhetoric. All right, rhetoric. All right, okay. Like, I think we're good now. I think that's enough words. R-H-E-T-O-R-I-C, rhetoric. Okay, great. All right, so now let's run our tests. Okay, we'll run this thing, and it should all fail, right? Respect isn't valid either. Is it not valid? Okay. Assert false. Okay. Again, I'm just taking your word for it. I don't have the thing in front of me. All right. So we've got a bunch of falses and a bunch of trues, I hope. And we'll run this thing. Run this test. Run test Boggle. And it should fail. Okay. And that's the idea. It should fail first. Okay. And it did. And how did it fail? It just said null pointer exception. Where did it fail? Boggle 43. Okay, that's because it's returned null. What we could do is return an empty set just to make it a little bit more polite. Return new array list. Like that. Just do that. So return an empty one. So it's not null, but it's empty. There's nothing in there. Okay, and now it shouldn't have a null pointer exception, but just should say nothing's there. And it says did not contain press, which is exactly what we expect. All right, so we're off to a start. Now what we're going to do is another little bit of testing. Okay, what we're going to do right now is if you think about it, one of the challenges, and this is something that applies to a lot of your assignment work, is how do we move from one to the other? How do we know what our neighbor is? If you want to go from one dice to the next dice, how do you do that? Well, what would be cool is if you had a special little data structure that told us that if I'm this one here, then my neighbors are that one, and that one. So let's do that. Let's give everything a number. We'll start off here at 0, 0, 1, 2, 3, 4, 5, and so forth, down to 15. And then what we want is an array where we can say, okay, we're at 13 here. We're at 13, and what are the neighbors of 13? And you can say, well, the neighbors of 13 are 12, 14, 10, 9, and 8. So 8, 9, 10, 12, 14 are the neighbors of 13. All right, so let's write ourselves a little data structure. It's going to be really useful later in the game that tells us who our neighbors are. Okay, and let's do that, and we'll write ourselves some test functions. Okay, so we'll write a test for that as well. So we've got some notes here on that. Let's write ourselves some tests. Okay, so first of all, we'll start off with a test. At test public void test neighbors like this. And what we're going to do is we're going to have ourselves a static class up here, a static data structure here. What type we're going to give it? Well, we're going to make a list of sets. Okay, so what we're going to make is a list of sets. All right, so a list of sets. So this what that's going to mean is that for every, let's have a look at this in the picture. Okay, so what I want to make is a list. That'll be element 0, that'll be element 1, and then for every element I want a set of all of the neighbors. All right, so a list, one for each element, the 16 element long list, and for each of these there should be a set, and that set should be the set of all the neighbors. All right, you got that? So we're going to make a list of sets. So we're going to make this thing here static. We'll just declare it static because this is something which is never going to change. List, and every Boggle will use it, right? So if we make different Boggles, it's still going to use this thing. Hash map of integers, right? So making a list of hash maps of integers. Everyone get that? We can just make hash sets. I mean, let's call them sets. In fact, you don't even need to say whether they're hash sets or not. Set of integer. Okay, so it's a list of sets of integers. All right, and yep, include that. All right, so we're going to make this thing, and we're going to call it neighbors. Right, like that. H in there. Whoop, what's going on here? Missing a H. All right, neighbors. And at the moment, it's just going to be empty. It's going to be an array list. Array list. Like that. Of hash sets. Sets of integers. Okay. And the length, the size of this list will be the number of dice. Okay, so we need 16 of them, right? So this is a list of sets. Okay, for every dice we have a set of who its neighbors are. So dice.length, like that. Okay. So we've just created that. We haven't initialized it. So at the moment there's no information there at all. Oops. Okay. So now we're going to test this set. We're going to write the test for it and see if it has the right information in it. So we're going to say what should be in the set and what shouldn't be. For one thing, remember what we're going to do is when we're on a particular dice, we're going to say go to our neighbors. Okay. One thing that shouldn't be there is ourselves, right? Because we are not a neighbor of ourselves. Okay. So one of the first things we can do is say assert false, like that, and we can say included self in neighbors, and then we'll just say neighbors dot get if we get ourselves or get anything like 1 dot contains 1. Okay, and we could run the 16 times too. We can do this. So for int I equals 0, I is less than 16, I plus plus and then we can say, change this thing to say I. Okay, so it should always not have I and I. So we should not be in our own neighbor set, right? That's the first one. What other things can we say there? We can say it should never be a negative number, right? We can just test for a negative number. These are things which we can test for all of them, right? So let's just do this. Oops, like this. We can just copy and paste this. We don't want to have -1 in there, okay? Okay. There's lots of things we could test. By the way, hopefully one of the things you'll appreciate as we do this is one of the things you'll appreciate as we do this. It's really hard to write good tests, okay? And I'm sure some of you will poke holes in these tests. So the word we use in computer science is coverage. What's the coverage of our tests? Do we have good coverage? Are we covering a lot of examples? Okay, are we covering all the important ones? Okay, so so we do not want to include -1 in any of these. Okay, like that. And then we can do the same for what? For anything. We can just have another example here and put in here. We can't have 16 in here either, right? 16. Okay, that's ones that none of them should have this true. Then we can write some specific ones, right? So we can do some assert true ones. Assert true. Now we can write some very concrete examples. Oops. Did not include something. So 0 has to be a neighbor of 1, right? So in neighbors. So let's use that as a concrete one. We won't do it for everything because some of them will have shouldn't have 0. Only some of them should have 0 as a neighbor. Okay. So we'll say did not. If I go to 1, it must have 0 in it. Okay, as a neighbor. All right. So that's a test. It says if we get this right, then it should have 0 as a neighbor of 1. We can write some more here. Let's just quickly write a couple more, then we'll try and finish this off. So let's just do a whole bunch for 1, okay? So what else are the neighbors of 1? Any other suggestions? So 1 should have 0 on one side, 2 on the other side, right? What else should it have? Let's go back to the picture. Okay, so this is 1. Sorry, this is 1, whichever way you want to count. So 0, so that's 0, that's 1. So it should have 2 and 0 and not 3, but it should have 4, 5, and 6. Okay, so let's put them in. 4, 5, and 6. Four, 5, and 6. All right. I think we're going to leave it at that for now. We've written quite a few tests. This is not perfect by any stretch, but it's a start. And again, partly what I'm doing here is illustrating to you the actual difficulty of writing tests. Now let's actually write this, set up this data structure. And once we've done that, we might stop and we'll resume the next day. So what we're going to do here is we're going to write this actual data structure. And to make it easier, I'm going to write a little thing, which is the distance. Int array, we're going to call it distance. And if you notice, let's go back to the diagram, so that if you take one that's in the middle like this, you'll notice the distance to that one is -1. The distance to that one is +1. The distance up here is plus 1, 2, 3, 4, 5. And the distance down here is -1, -2, -3, -4, -5. That's the distance to anyone that is not on the edge. Now you've got a special case when you're on the edge, because one like this doesn't have stuff that's off the edge. But all the other ones, so as long as it's not off the edge, you should have something that is -5, -4, -3, -1, +1, +3, 4, and 5. Okay, so that's the neighbors. So let's write that down. Let's write some code that says that distance equals this little array here, -5, comma -4, comma -3, -1. plus 1, plus 3, plus 4, and plus 5. Okay, so that's the actual neighbors for any of these dice, except the case where it goes off the edge, right? Hang on, I don't like those red squiggly lines. Let's fix that up, like that. What? Array list. What have I done here? Integer type, included. What's going on? Sorry. It should have just imported them. Okay, why is it not doing that? Anyway, I'll come back to that in a second. I'm not sure why that's behaving badly. IntelliJ is not being friendly to me. So now let's go through all these things. So for int I equals 0, I is less than 16. Oh, come on, keyboard. I plus plus. We're going to go through each of the 16 dice, and they're each going to have those in their set, except if it goes off the edge. All right. So we're going to say. So we're going to create a new hash set for this. We're going to say we can do the following. You can call it this set of integers. Right. This is the set for this particular one for this die equals a new hash set. Notice. Here, I've used the interface type, which is set, which is abstract, and well, it's the interface type. And here, I've used a concrete one, which is a hash set. Okay, so I'll create an empty hash set. Okay, now what we're going to do is for each of the distances, we'll add that in, unless it goes off the edge. All right, so let's just do that. So for int d in distance, like this, do the following. Oh, I know what was wrong here. I forgot to type new. I was wondering why on earth isn't that behaving. There we are. What's going on now? Change new to... okay. Okay. Now what we're going to do is we're going to go through all these things here and add it in. Say our neighbor is going to be int n equals I. That's us here. We're going through all of them. Plus the distance. Right? And then we just have to check if it's legitimate or not. So if it goes off the edge... then it's not legitimate, so we don't put it in the set. If it otherwise, we put it in the set. All right. So we can just say die dot add n. We could do that, but we can't do that for all of them because they might be off the edge, right? So let's just check that. If we're one of these ones here, those notional neighbors over here don't actually exist because they're off the edge. So we mustn't include those ones. And likewise for this one, it's only actually got 3 real neighbors. Okay, it's just got those 3. It doesn't have all the others. Whereas this one in the middle here has got all of these neighbors. It's got 8. It's got 3 there, and those 2 there. All right. So what we need to do is we need to not do that adding unless they're actually not going off the edge. And the way we can do that is find out which column we're in. How do we find out which column we're in? Let's find out which column our neighbor is in. So int n col, that's our neighbor's column, equals n integer remainder of 4. Right, because it's a 4x4 grid, and int n row is n integer division of 4, right? So it's a row in the column. And then what we need to do is we need to say if our neighbor is greater than 0, greater than or equal to 0, greater than or equal to 0, like this. So if it's less than 0, we don't want to, it's not one we're going to include. If it's that, and it's less than 15, and we're in the, the difference between our columns, right? Our columns have to be the same, right? So we just say if our column, we can't be more than one column away from each other, okay? So we say math dot absolute value of the our column and column. Actually, I should have said this. What I should have done is this. We don't need to do it the way I wrote it. Let's do it this way. Okay, so n column is the column that the neighbor is in. I column is in the column we're in. and they should only ever be different by 1. If they're not, then we've gone off the edge. All right, so we can just go like this, n col minus I col must be less than or equal to 1. If it's greater than or equal to 1, then we've made a mistake. Less than or equal to 1. If that's true, then we can add it to our set. Okay, and then finally we need to add our set to the list. Okay, so down here we say neighbors dot add die, and we're done, hopefully. So now let's test this. I forgot now if we actually tested it before I wrote the code. We should have, but I might have forgotten. Looks like we didn't. Okay, it worked. Let's just comment this all out just to make sure. Oops, wrong keystroke. Like that. Comment them all out like that. So it's all gone. We run this again like this. Run. And they all fail. Okay, so indeed our test did do the right thing, and indeed our neighbors works. So now we're in a great position to solve Boggle, right? Because we've got this nice little thing here which tells us where our neighbors are, which is going to allow us to walk around that Boggle board and find the words. And we're going to do that on Monday. And with that, we'll finish up. So thank you and have a great weekend. And yeah, talk to you later.